Today on Dino Diladon, I have in for repair a Luminance 12,000, which is a show laser that's manufactured by Goldenstar. And the issue with this laser is that after a while, the blue no longer works until you turn the brightness down, and then it comes back to life. So this certainly sounds like an overheating issue somewhere inside of the unit. My likely culprit, I would say, would be a failed thermal electric cooler on the inside of the blue laser head, although it could be a variety of issues, such as a failed component on the laser driver itself. For example, a bad operational amplifier, resistor somewhere on the board, or even the MOSFET that turns on the thermoelectric cooler could be bad. So we're going to have to go ahead and diagnose which one of those possible issues it could be. And the first step is, of course, power up the laser and get it going. Well, let's go ahead and flip it around. Uh, we can go ahead and ignore the LCD light. That's interesting. Key switch and interlock. That's going well. We'll put that on the interlock out, I suppose, because that's our only option. Let's go ahead and see if the key even works in the right place. Hey, what do you know? That works. Finally getting somewhere. All right. Power. Test card first. Let's go ahead and pop that in. So I'm going to put in an SD card that has some test patterns, and we can use the FB4 to view. Go ahead and see what the problem is with the laser without connecting it up to a computer, which is kind of nice. Turn it on. Make sure the output window is open. All right, here we go. Test mode. Brightness 19, master size 20, excellent. Enable laser, and we have output. Go ahead and turn up the brightness. We'll just let this run. If it cuts off real quick, then it's probably going to be a driver board problem since the parts are physically smaller. It'll take less time to heat up. If it takes, say, more than 5 or so minutes, I'm going to guess that there's a problem with the thermoelectric cooler on that driving circuit. No. Go ahead and see. Let's just go ahead and set it on blue. That way we can get a better idea of what's going on. Color settings. We don't need any red. Turn that down. Green. Turn that down. All right. There's our blue. And now we wait. Wow, that was really quick. That only took about 20 seconds. Yeah, I'm thinking that it's a problem with the driver board, given how quickly it failed. So let's go ahead and turn off the laser, open it up, see what the problem is. What did I do? Glue that one in? That's terrible. Now we're finally getting somewhere. Does this have a safety interlock switch on the inside? No. All right, now that we're inside of the laser, let's go ahead and see what the parts are and get a little bit more of an idea of how they're connected. Go on and start troubleshooting from there. Well, looks like we have two identical power supplies up here. One here, one here. Those are probably 24 volts apiece, and they're probably also in series, giving us the positive, negative 24 volts required to drive the galvanometer. So these two power supplies will probably be connected to the galvanometer amplifier here. And then it looks like we have 3 more power supplies. 1, 2, 3. I'm betting that each one of those are for a color inside of the laser, given that there's also what appears to be 3 laser drivers. So 1, 2, 3, which actually makes this a little easier since we have separate power supplies and separate laser drivers to work with, and we're not dealing with just a one does everything type of situation. So that's kind of nice. I think from here, the best thing to do is to turn on the blue and see if any of the power supplies fail. It looks like each one of the power supplies has a little blue indicator light. I see one right here, one right here. Where's the other one? Oh, I see it right here. Okay, so 1, 2, 3. We have those 3 LEDs that we can watch. See if the power supply itself fails or not. Go ahead and turn on the laser. Test mode. And enable laser. Go ahead and turn off the shop light so we can pay attention to those blue LEDs. Once again, 1, 2, 3. See which one fails, if it fails at all. Turn out the brightness. Alright, and now we wait. Alright, the laser shut off, and all the power supplies are still on, so not a power supply issue. What's the next culprit? Let's see, turn on the brightness. Restart the laser, see if it comes back on right away. Nope. Hard restart. Interesting. You fail right away again? Alright. So I think what I want to do now, since the blue turns off, I want to run just the green lasers just to make sure that the problem is isolated to just the blue, and that's not just the first color that turns off. So I'm going to go ahead and turn down the brightness. I'm going to set the color settings so we only have green. So turn that on. Blue, turn that down. Alright. And turn up the brightness. See if green shuts off. That way we can see if it's a global problem with the laser head on the inside overheating and cutting off the thermistor, or whether it's just blue related. I'm going to turn on the red too, just to get some more heat going. Right, well, it doesn't seem to be an issue with the optical deck overheating, so I think further investigation needs to happen. I don't necessarily want to remove the laser drivers right now. I do want to verify another thing. So I did notice that the overall color balance of the laser is a little blue underpowered. Also, I'm noticing 3 dots for green, and I want to say 6 for red, and only 1 for blue. So I have a sneaking suspicion that on the inside of the laser head, we're going to find a bad blue. I'm curious to see whether that's the case or not. So I'm going to go ahead and shut down the laser. We'll take off this side panel right here. We can go investigate on the inside of the laser head, see if we in fact do have a bad blue. If we do, that could be generating more heat in a specific area, and that could need to be replaced. But let's go ahead and quick verify that. We'll come back once I have those pieces taken off. At this point, I'm just about ready to take off the top of the laser head. And there's going to be 2 things that I'm going to be checking. First of all, I really do want to check if there's a bad blue laser diode. I have my suspicions that there might be. Second thing is I want to see if the area by the blue laser diodes is getting unusually warm, and if that's an issue. So the 2 things of importance. Go ahead and remove the top of the laser head. Once again, if you're going to be working on your laser, always remove the top of the laser head as vertically as possible, so that way you do not hit any of the delicate optics on the inside. The fan here helps, makes a nice little grip. Oh, that comes off real nice. All right, here, let's see what we have. Okay, it looks like we have 4 red, 3 green, and 1 blue. I'm guessing that these are going to be the reds. They obviously use open can diodes, given that there's a piece of glass on the front. That's nice. I like that better than OPT. And brass on brass. This is actually a pretty nice unit. I don't really see anything major to complain about. That's cool. Let's go ahead and turn on. But yeah, so 4 reds, 3 greens, and 1 blue. Pretty straightforward. Enable laser. Sure is. All right. Go ahead, test the blue. Color. Turn the red down. Turn the green down. The blue up. Turn the blue up. Brightness 100%. That's helpful. Blue wasn't even running. Reset the laser. Test mode. Enable laser. Brightness 100%. Color settings. Yeah, blue should be on. That's interesting. Optical deck really isn't that warm either. Where'd blue go? Green, blue. Okay, so this is a blue driver for sure then. Ha! Blue isn't turning on at all now. Interesting, interesting, interesting. Yeah, the thermistor too is right close to the blue right here. No. Are there any thermistors? Yeah. Okay, so each color has its own thermistor too. That's interesting. Alright, so I want to run the laser at a pretty high brightness. I want to see if the optical table heats up any more than it should at this point. The green are some of the least efficient laser diodes, so if the TECs underneath here are failing, we should see most of the heat generated in the center of the optical deck, where the greens are. Yeah, the section by the green is marginally warm, but we're not going to any kind of thermal runaway condition. So the thing I want to do, given that each laser color has its own thermistor, I want to point that out to you. That way you know what I'm talking about. So I'm going to tilt the laser up a little bit so you can see the inside. All right, so we got these things called thermistors, and they detect the temperature of the area by the laser diodes. We got this one right here. That's probably for the blue. We got one. Let's see. Got one over here. That one's for the green. And then we have one over here. That one's for the red. So my next plan is to figure out where the wires go for the blue thermistor, and then we're going to go ahead and play with that value on the actual driver board. So they're probably 10K thermistors. So I'm going to find that. I'm going to put a 10K potentiometer on there, probably a 20K, and these are NTC. So if the thermistor gets hotter, the resistance goes up, and if the part gets colder, the resistance goes down. No, vice versa. Sorry. If the part gets hotter, the resistance goes down. Part gets cooler, the resistance goes up. So I'm going to go ahead and try and spoof the driver, see if it's a problem with the thermistor, that calibration not being set right. As long as we don't enter a thermal runaway condition, we can go ahead and tweak that value a little bit, make sure the laser doesn't shut off, and still operates in a good, healthy temperature range for the laser head. Well, that's the next plan. Well, I found something interesting, but I don't think it's something to get excited over. Let me explain. So here's the driver, and if you take a look here, the pins are actually labeled. So here's the laser diodes, positive and negative, got 5 volts here, ground, and RT positive, minus. And if you look at RT positive, you'll notice how far the screw is actually unthreaded. So that means that connection is loose. Now these are NTC thermistors. So the way they work is if the laser is getting colder, they become less conductive. If the lasers are getting warmer, it becomes more conductive. So here's the catch. If this gets disconnected, it actually shows it as a higher resistance and fools the laser driver into thinking it's cooler than it actually is. So it would actually be worse to have a short here because it would think it was an overheating condition instead of having this loose. So tightening the screw down, I expect to change absolutely nothing. But we're going to go ahead and do it anyway and see what the results are. That looks better. While we're here. All right. Let's go ahead and see if the blue fails again. Turn on the laser unit. It would be nice if that was a fix, but I doubt it is. Here we go. Testing a hunch. I'm going to go ahead and turn off the light. That way you can take a look at the beautiful laser colors in all their glory, at least until it fails, which I suspect it will. But hope springs eternal. 100%. And now we wait. Well, so far so good. I'm going to throw the top of the laser head back on and the rest of the case pieces loosely just to kind of trap in some of the heat a little bit more, see if it fails, and run it for a while. But that could have been the issue, surprisingly enough, that loose screw. Well, the laser's been running now for about an hour and a half and hasn't had a problem with the blue cutting off. So it looks like the issue was solved by tightening the screw holding the wire in the terminal block for the thermistor. So that was a nice fix. I'm going to go ahead and put the screws back in. So before I do, we can just take this right out. We don't need that. Remove the fan too. Won't need that either. Yeah, that's it. It's done. And then there's another laser that the client sent in that needs an alignment. So I'll go ahead and do that after I get this laser put back together. That's suspicious. And now for my favorite part, doing the alignment on the inside of the laser head. So once again, if you're taking the cover off of a laser like this, you want to take and lift the cover off as smoothly and as vertically as possible. So that way you don't hit any of the delicate optics on the inside of the laser. Let's go over the entire optical path. We have 4 red lasers here, and each one of those red lasers are beam corrected and collimated using these 3 cylindrical lenses. So that gives us 4 beams coming out of this section here that are red. You have these 3 lasers here. Those are green. Once again, they're collimated by these 3 cylindrical lenses. We have these little mirrors right here, and we have 4 mirrors right here. Those are knife edging mirrors. And so what happens is, for example, the red come out this way, get reflected off roughly at 90 degrees, and come out this way. The green lasers that come off get reflected off these 3 mirrors, and they come off this way, and they get bounced off this optic. So the red goes through that optic, the green bounces off, and these 2 optics right here, therefore mixing the colors, they're called dichroic filters, dichroic mirrors. So the green comes down this way off these little knife edging mirrors here, bounce off this way. We got a blue laser right here, same thing, 3 lenses to do the collimating, little knife edge bounce mirror here, that sends the output this way, and that blue gets reflected off this dichroic mirror right here, out this way. So all the red get bounced off these knife edge mirrors through the 2 dichroic mirror filters. The green all come out this way, get bounced off these mirrors right here, bounced off this dichroic mirror right here, out this way. And the blue comes through this way, hits that bounced mirror, comes off this way, bounces off this dichroic filter, and out. There are 3 main types of adjustments you can do on the optical mounts. So each one of these optical mounts, you can move them in and out like this. They do have kind of a horseshoe cutout around the screw, which allows you to take this whole optical mount and move it in and out, say about 3 millimeters. That takes and moves the beam like this and allows you to get those beams real close together. The next adjustment you can make is the rotational adjustment, and that's on the horizontal. You'll notice on the back of a lot of these mounts, inside of lasers, there's actually a little hole here in the back. And so what you do is you put the tool in the hole, and you can loosen up that screw if you need to, but you put the tool in the hole in the back, and you can rotate the optical mount like this, and that will move the laser beam side to side accordingly. The last adjustment you can make is the vertical adjustment. So if you see there's another little hole right here, you stick the tool in. The actual knife edge mirror is on a little brass block. You can see it kind of clearly here, but you can take and rotate the tool back and forwards like this, and you can actually set the height of the laser. So that adjustment will take and move the beam up and down like this. So those are the three adjustments you can make with these optical mounts. If you're doing just an alignment, realignment, and a laser, normally you don't have to worry about this strafing, moving in and out. Usually that's pretty fine, but we'll be focusing on the horizontal and the vertical rotation. So where we stick the little tool in a little hole, give it a little bend, and make sure the angles are as perfect as we can get them, so that way the beams line up. Another thing to note is if you're doing an alignment and you're bouncing the output of the laser head off the galvanometers like we are doing in this situation, you have to translate the movement of the beam on the inside of the laser by 90 degrees. So what that means is if I say take this optic and I do the vertical and I move the beam up and down, it's actually going to go side to side on our final output image. And that has to do with the reflection geometry off the galvanometers. And the same is said for if I go and do a horizontal adjustment. So if I take and move the optic like this, moving the beam back and forth like this, it's actually going to move the beam up and down on the final output image. That's what I mean by you have to translate it by 90 degrees. So keeping that in mind, I'll go through the rest of the setup. I'll be running the laser with input from Quick Show 3, and I want a stationary white dot, so that's what my output will be. I have a bounce mirror about 40 feet away, giving me a total of about 90 foot. Yeah, reasonable bounce. That's the first surface bounce mirror, but at this distance, it really doesn't matter. And then I'll be looking at my final output image on this white piece of material that I hung up right here. So I'll have all of my outputs right here, and I can see them. I'm right next to the laser down here, and that way I can see my output clearly, and I can see what I'm doing clearly. The other thing is that the way I have it set up, my eyes can't see the bounce mirror, which means that there's relatively little risk of me getting hit by the reflection coming off the laser. If I can't see the mirror can't see me. So it's a pretty safe way of doing things. I'm going to set up the camera, and I'm going to start in with the alignment. Now that I have the laser fully set up to do the alignment, I want to show you one more thing before I get started. So I like to use these translucent, non-reflective pieces of plastic to block the laser beams on the inside of the laser head. And these are really great. So they're non-reflective, which means that if I use them to block the laser beam, I don't have to worry about the laser beam getting reflected and then sent back into the laser diode, which could damage it. I also don't have to worry about the material getting hot and burning because I'm not actually blocking the laser beam. I'm diffusing the laser beam. So the energy is not being absorbed by the little piece of plastic. I don't have to worry about it burning or getting any kind of contaminants on the glass optics. So it's a pretty good thing to use if you're going to block a laser beam. We got our output here. We got the blue, got all the greens, we got the reds. So what I'm going to do, I'm going to start by blocking out the blue and the green. No, put our little translucent piece of plastic there. That's the blue. Take another one, block the green. And we're stuck with our reds. So, boom, boom, boom. Let's see where all the reds are. So, block the first one. Right here. Second one. Right there. Third one. Down there. Fourth one. Alright, seems like the first one and the fourth one are pretty evenly aligned. So let's go ahead and do the alignment on the two center ones. Looks like they both need to come up, which is going to be rotational adjustment on the inside of the laser because of that translation. So let's see how these move without changing the screw. All right. Bring that one up just a little bit too. And then we'll touch up the vertical, which will be the horizontal position, once again because of the translation of the galvanometers. Meters. But we're going to have to bring that one up a little bit more. Just like that. Perfect. Now let's block out the reds and focus on the greens. Want to see where those greens lie. So let's block them off individually. So that's a little low. All right. Their vertical output is a little off, which means that I'm going to have to do the alignment once again rotationally on the horizontal. So let's go ahead and do that. Yep. And then the blue is just a single output, so we can go right to the Decrook mirrors for that. So it looks like the red's going to be our stationary beam, so we don't move the location of that. Let's go ahead and move the location of the green output. So it looks like it needs to come over, which is going to be a vertical adjustment on the inside of the laser. So stick in the top like this, rotate it. They cut that mount just a little, there, they put that hole in just a little low. Can't get the tool in there. Can we move it with the finger? All right, get the tool out. Can you grab me a pliers? That looks really good. And now for the blue. So it looks like we need to do both horizontal and vertical. Let's do the vertical first, which is going to be the horizontal. I'm going to move the blue over this way, which will be an adjustment on the vertical portion of the mount. I say that's pretty line. Let's check it out again. Maybe we can move screen over just a little bit. No, that really is how the green looks. Okay. Now, little touch up. Little touch up. I think the green comes down just a little bit. Yeah, that's perfect. Perfect. And then just because it looks aligned doesn't mean it's necessarily going to stay aligned. So I'm going to let the optic sit for about, say, 2 or 3 hours. I want to see if any of the adjustments walk during that time. If they don't, maybe put a little dab of epoxy on all the optics just to make sure they don't, and close it up. Yeah, these things still look so cool. Well, now there's only one more thing to do, and that's quality control. I hope you enjoyed the video, and as always, stay tuned for more.